Hello everyone, welcome to today's presentation. I'm excited to introduce our topic, wastewater sedimentation and flotation. In this session, we'll explore how raw wastewater is treated, focusing on the initial steps of sedimentation and flotation. We'll cover how materials settle or float, the role of collection systems, and the primary clarifiers that kick off the treatment process. Let's get started. Now, let's take a closer look at what happens inside a primary clarifier. The main goal here is to dramatically reduce the wastewater's velocity. When the water slows down, solids have a chance to settle out to the bottom, while lighter materials like oils and grease can float to the surface. This process is essential because it helps clarify the wastewater before it moves on to the next stage of treatment. In a typical clarifier, the settled solids are then scraped towards collection sumps. In rectangular designs, they're directed toward one end, while in circular ones, they're collected in the center. From there, these solids are pumped to sludge handling systems for further processing. Overall, the primary clarifier plays a crucial role in removing the bulk of the solids early on, making the subsequent treatment steps more efficient and effective. Let's take a closer look at primary versus secondary clarifiers. Primary clarifiers are positioned right after the bar screens and grit channels, making them the very first step in the clarification process. Their main role is to remove settleable solids from the incoming wastewater, and because they handle the initial load, the sludge they produce is quite dense. This step is crucial because it helps to separate out the heavier solids early on, setting the stage for the biological treatment that follows. Now, moving on to secondary clarifiers. These come after the biological treatment processes, where microorganisms break down organic matter. The secondary clarifiers are responsible for removing additional solids that are produced during this biological process. The sludge here is less dense compared to primary sludge, and the effluent that leaves this stage is much clearer, which is essential for meeting environmental standards. Overall, understanding the distinction between these two types of clarifiers highlights how the treatment process is carefully staged, from removing the heaviest solids early on to polishing the water after biological treatment, ensuring the water leaving the plant is as clean as possible. Let's take a closer look at the clarifier components and their functions. First, the influent control. Gates and channels play a crucial role here by transporting and distributing the wastewater evenly across the width of the clarifier. This even distribution is essential to prevent short-circuiting, which can compromise the treatment process. Moving on to the settling zone, we use target baffles to spread the flow uniformly. This helps the particles settle more effectively. Effluent weirs are also important. They ensure that water flows out evenly and give us the option to adjust the water level as needed, maintaining optimal conditions for settling. Next is sludge collection. Main collectors are responsible for dragging the settled solids down to the sumps, where they can be removed. Cross collectors help prevent bridging, where sludge gets stuck, by moving the sludge to designated removal points efficiently. Finally, scum management involves skimmers that collect floating materials like oils or grease. These are then moved to scum troughs. Baffles are installed to prevent floating debris from reaching the effluent, ensuring that only clean water exits the system. All these components work together seamlessly, supporting the overall efficiency and effectiveness of the clarifier. Let's talk about calculating clarifier efficiency. In process control, it's essential to measure how well our treatment is working by comparing the water quality indicators before and after treatment. To do this accurately, we collect 24-hour composite samples, which give us a representative picture over a full day. We focus on parameters like BOD, or biochemical oxygen demand, and suspended solids, because these tell us a lot about water quality. Now, the core of this process is the efficiency formula. It's calculated as the difference between influent and effluent values divided by the influent value, then multiplied by 100% to get a percentage. This tells us how effective our treatment process is at removing contaminants. Let's look at an example. Suppose the influent BOD is 200 milligrams per liter, and the effluent BOD is 140 milligrams per liter. Using the formula, we subtract 140 from 200, which gives us 60. Then, dividing 60 by 200, we get 0.3, and multiplying by 100% results in an efficiency of 30%. This example clearly shows how we quantify treatment performance, and understanding these calculations helps us ensure our process remains efficient and effective. Let's take a closer look at the expected removal efficiencies in the treatment process. For settleable solids, we're aiming for about 95% removal, with actual efficiencies ranging from 95 to 99%. This means most of these larger particles are effectively settled out. Moving on to suspended solids, the removal efficiency is generally around 50%, but can range from 40 to 60%, depending on the specific conditions. When it comes to BOD, or biological oxygen demand, the removal can vary quite a bit, anywhere from 20 to 50%, highlighting how organic matter reduction can depend on various factors. For bacteria, removal efficiencies are typically around 50%, but they can range from 25 to 75%, reflecting the importance of microbial activity and treatment conditions. Total solids removal tends to be lower, around 12% on average, with a range of 10 to 15%. An important point to remember is that the pH usually stays between 6.5 and 8 and doesn't change much through the clarifier. Keep in mind, these efficiencies are influenced by several factors: wastewater characteristics, flow rates, mechanical conditions, and whether the sludge is properly withdrawn. All these points are key because they show us how effective the clarifier can be under different conditions and what factors we need to monitor for optimal operation. Now, let's take a look at some of the key factors that influence the performance of a clarifier. First, we have wastewater characteristics. The types of solids present in the wastewater can vary significantly, and this affects how well the solids settle out. Industrial waste content is also critical, since different industries produce different types and amounts of solids. The age of the wastewater matters too, as older wastewater might have more stable solids, making separation easier or more challenging. Temperature variations are another factor. Lower temperatures can slow down settling rates, impacting overall efficiency. Moving on to operational factors, hydraulic loading rates are essential because they determine how much water flows through the clarifier at a given time. If the flow is too high, solids might not settle properly. Mechanical conditions, like the state of the clarifier's mechanisms, also play a role. Well-maintained equipment ensures optimal performance. The cleanliness of the clarifier itself is important, as buildup of sludge or debris can hinder operation. Additionally, the timing of sludge withdrawal needs to be carefully managed to prevent solids from short-circuiting or re-entering the clarified water. Finally, we have process interactions, which are the connections between different parts of the treatment system. Returned activated sludge, digester supernatant, centrifuge centrate, and filtrate all influence clarifier performance. These streams can carry additional solids or nutrients that affect the settling process, so understanding their interactions helps optimize overall treatment efficiency. All these factors are interconnected and highlight the importance of a comprehensive approach to maintain the effectiveness of the clarifier within the wastewater treatment process. Let's talk about sludge and scum pumping. First, it's crucial to remove settled particles regularly to prevent septic conditions. The frequency of removal isn't one-size-fits-all. It depends on various factors like the system's conditions. Typically, intervals can range from every 30 minutes up to 24 hours, and experience really helps determine the optimal timing. Next, recognizing septic conditions is vital. Septic sludge often produces gas, which causes clumps to float. It also tends to be odorous and acidic, with a low pH. These are good signs that septic activity is happening and need attention. When pumping thick sludge, aim for a dry solids content between 4 and 8%. It's important to go slow during withdrawal to avoid pulling excess water, which can dilute the sludge and complicate removal. Finally, always monitor the quality of the sludge during pumping. Take samples frequently and stop the process once you see that the sludge has become thin, meaning it contains excess water. This ensures you're removing the right amount without overdoing it, maintaining the overall health of the system. Let's talk about some key design factors that influence wastewater treatment, specifically temperature and short circuits. First, temperature effects. As water temperature increases above 4 degrees C, the settling rates of particles tend to go up. This happens because warmer water is less dense, which enhances the difference in density between the water and the particles, making them settle faster. Conversely, colder water is denser, which reduces that density difference and slows down the settling process. So, temperature plays a crucial role in how efficiently particles settle out of the water. Now, moving on to preventing short circuits. It's essential that wastewater is evenly distributed across the entire tank cross-section. If there are areas with high velocity, particles can be carried through too quickly, reducing detention time and preventing proper settling. To avoid this, we use features like weir plates, baffles, and carefully designed inlets. These help ensure the flow is uniform and prevent short-circuiting, which is vital for maintaining effective treatment. Connecting these points, managing temperature and flow design are both critical in optimizing settling and overall system performance. They help us ensure that the treatment process is efficient, reliable, and consistent. Now, let's take a closer look at some critical design parameters for clarifiers. First up is detention time. This is essentially how long the wastewater needs to stay in the clarifier for particles to settle out effectively. Most engineers aim for a detention time between 2 to 3 hours, which is calculated based on the flow rate and the size of the tank. Getting this right is key to ensuring proper removal of solids. Next, we have the weir overflow rate. This measures how many gallons flow over a lineal foot of weir per day. The typical recommended range is between 10,000 and 20,000 gallons per day per linear foot. However, for secondary clarifiers, or when high effluent quality is required, lower overflow rates are often necessary to prevent solids from escaping. Moving on to the surface loading rate, which is expressed as gallons per day per square foot of tank surface area. Properly managing this rate helps prevent overloading the clarifier. Common suggested rates range from 300 to 1,200 GPD per square foot, depending on the nature of the solids and the specific treatment goals. Finally, let's discuss solids loading. This refers to the amount of solids removed daily per square foot of the clarifier surface, usually expressed in pounds per day per square foot. If this exceeds the design values, it can lead to increased solids in the effluent, which compromises water quality. Understanding and balancing these parameters is vital for designing an effective clarifier that meets treatment objectives and ensures consistent, high-quality effluent. Now, let's talk about secondary treatment, specifically trickling filters. This stage is crucial because it focuses on removing very small suspended solids and dissolved solids that primary clarification simply can't capture. Essentially, it helps us clean the water even further by targeting those tiny particles and dissolved materials. What's important to remember is that this process can achieve an overall removal efficiency of 90% or more for suspended solids and BOD, which is a significant improvement in water quality. Trickling filters are one of the 3 common methods used in secondary treatment, alongside rotating biological contactors and activated sludge systems. Each of these methods has its own advantages, but trickling filters are particularly effective because they create a biofilm that breaks down organic matter as the water trickles through. Connecting this to the overall theme, secondary treatment like trickling filters is all about refining the water after primary clarification, ensuring we remove the tiny particles and dissolved substances that could still harm the environment if left untreated. Let's take a closer look at the trickling filter structure and its components. There are 3 basic parts that make up these systems. First, we have the media and retaining structure, which provides a surface for beneficial biological growth to occur. This is where the microorganisms break down the organic matter in the wastewater. Next, there's the under-drain system, which collects the treated water and also allows air to circulate, supporting the aerobic processes. Lastly, the distribution system evenly applies the wastewater over the media, ensuring uniform contact and treatment. Most trickling filters are designed as large, shallow, cylindrical structures. They are typically filled with media like stone or plastic, which serve as the surface for biological activity. These media can vary: rock, slag, coal, bricks, redwood blocks, or molded plastics. For example, rock media usually measures about 2 to 4 inches in diameter and is installed at depths ranging from 3 to 8 feet. On the other hand, synthetic media can be much deeper, sometimes 15 to 30 feet, especially in taller filter towers. Understanding these components and their design helps us appreciate how trickling filters effectively treat wastewater by maximizing contact between the water and the biological media. Let's take a closer look at how trickling filters actually work. The term filter might be a bit misleading here because solids aren't actually removed by straining like in a traditional filter. Instead, what happens is that as wastewater flows over the media, a biological film forms on its surface. This film is made up of bacteria, protozoa, and other microorganisms, creating a kind of gelatinous coating. This biological growth is key because it absorbs and uses organic matter, both suspended and dissolved, that's present in the wastewater. So, rather than physically filtering out particles, the biological film breaks down the organic material through biological processes. As the wastewater continues to contact this film, it flows as a thin layer over the biological growth. During this contact, the microorganisms consume the organic matter, effectively removing it from the water. Oxygen also plays a critical role here. Air circulates through the media's voids, providing the oxygen necessary for the microorganisms to thrive and carry out their digestion process efficiently. And eventually, when the biological film becomes too thick, excess growth sloughs off and exits with the effluent. This natural sloughing helps maintain a healthy and active microbial community on the media surface. By understanding this process, we see that trickling filters rely on biological activity rather than physical filtering, making them an effective and natural way to treat wastewater. Let's take a closer look at filter classification and loading rates. First, we have standard rate filters. These typically involve rock media that is about 6 to 8 feet deep. They support heavy biological growth, including worms, snails, and insect larvae, which helps break down organic material. These filters can handle hydraulic loadings of 25 to 100 gallons per day per square foot, and they are effective at reducing BOD levels to as low as 20 to 25 milligrams per liter in the effluent. Moving on to high-rate filters, these are designed for higher loading capacities. They may use rock media, which can handle between 100 to 1,000 gallons per day per square foot, or synthetic media that can support even higher rates, from 350 to over 2,100 gallons per day per square foot. These filters are usually 3 to 5 feet deep and operate with a continuous flow and recirculation, which promotes more uniform sloughing and efficient treatment. Finally, we have roughing filters, which are used for very high organic loadings, often exceeding 100 pounds BOD per day per 1,000 cubic feet. These are typically employed to handle industrial wastes with strong organic content. Their main purpose is to reduce the organic load significantly, by about 50 to 70%, before the effluent moves on to subsequent treatment stages. So, overall, understanding these different filter types helps us optimize treatment processes based on the specific organic load and flow conditions we're dealing with. Recirculation is a key strategy we use to enhance filter performance. By bringing the filter effluent back into contact with the biological film multiple times, we significantly boost treatment efficiency and help maintain operational stability. This process increases contact time, meaning the organic matter has more opportunities to be broken down effectively. Another important aspect is organism seeding. We introduce active microorganisms into lower filter sections, which promotes better distribution of these beneficial organisms throughout the system. This leads to a more uniform biological activity and improves overall performance. Controlled slewing is also crucial. When flows are higher, it encourages uniform slewing or the shedding of excess biomass, which prevents ponding and ensures good ventilation within the filter. Lastly, recirculation helps with BOD dilution, which reduces the strength of the wastewater. This prevents excessive biological growth buildup, keeping the system balanced and functioning smoothly. All of these points show how recirculation not only improves treatment, but also contributes to a more stable and efficient process overall. Let's talk about troubleshooting ponding problems and how to address them effectively. First, understanding the causes is essential. Excessive organic loading is a common culprit, as it can clog media and reduce flow. Poor primary clarification also contributes by allowing more solids to reach the media, leading to ponding. Additionally, if the media is too small or non-uniform, it can cause uneven flow distribution, resulting in ponding issues. Fiber or trash accumulation on the media surface creates blockages, while rapid uncontrolled slewing can disturb the media integrity and impede flow. Excessive insect larvae or snails can also clog the media, further exacerbating ponding problems. Now, moving on to solutions. One effective method is spraying the filter surface with high-pressure water to dislodge debris and restore flow. Manually turning or raking the filter surface helps remove accumulated debris and debris buildup. Dousing the filter with chlorine at about 5 milligrams per liter for several hours can help eliminate biological clogging agents. Flooding the filter to keep the media submerged for around 24 hours can cause slewing of unwanted biofilms or debris. Lastly, shutting off the flow for a few hours allows the growth to dry out, which can significantly reduce clogging and improve overall flow performance. By understanding these causes and applying the right solutions, we can maintain efficient filtration and prevent ponding from disrupting our system. Let's talk about some common operational challenges we face and how we can effectively address them. First, odor control is crucial. When you notice foul odors, it usually indicates anaerobic conditions, so maintaining aerobic conditions in the collection system and primary units is essential. Check your filter ventilation systems regularly and consider increasing recirculation to boost oxygen levels. Also, keeping wastewater splash contained helps reduce odor issues. Next, managing filter flies, especially cycota flies, requires attention. These tiny insects thrive in environments that alternate between wet and dry. To control them, increase recirculation rates to prevent ideal breeding conditions, keep orifices clear, and apply approved insecticides carefully. Flooding the filter for about 24 hours every week can also disrupt their life cycle, and maintaining good housekeeping practices is always beneficial. When it comes to slewing control, the key is to manage buildup without letting it become uncontrolled. Increasing recirculation pumping weekly helps induce controlled slewing, which keeps the process manageable. Monitoring both soluble and total BOD levels can help diagnose if there are any issues with effluent quality, allowing us to respond proactively. In cold weather conditions, ice buildup can pose a real challenge, especially when spraying wastewater that freezes. In such cases, decreasing recirculation while ensuring the flow remains proper is important. Operating two-stage filters in parallel provides redundancy, and adjusting orifices can reduce spray and prevent freezing. Building wind screens or covers can protect equipment from cold winds, and breaking up and removing large ice formations helps keep operations running smoothly. Overall, understanding and addressing these challenges proactively helps us maintain efficient, compliant, and safe operations regardless of external conditions. Now, let's take a closer look at rotating biological contactors, or RBCs. These are a type of secondary biological treatment system that use rotating plastic disc media. The discs are quite large, about 12 feet in diameter, and are mounted on horizontal shafts that can be up to 25 feet long. As these drums rotate at about 1.5 revolutions per minute, roughly 40% of the media surface is immersed in the wastewater at any given time. What's really interesting here is how the biological process works. Organisms, or microbes, form a slimy layer on the plastic discs. These microbes feed on the organic matter in the wastewater, breaking it down. They also use dissolved oxygen from the air to sustain themselves. As the discs rotate through the wastewater, this slime grows and then sloughs off naturally, meaning it falls away and flows to secondary clarifiers for removal. One of the key advantages of this system is its simplicity. It's a once-through process, which means it doesn't require recycling of effluent or sludge. The microbes do their job, and the clean water continues on its way, making RBCs an efficient and straightforward biological treatment option. This method seamlessly fits into the overall treatment process, helping us achieve effective organic matter removal with minimal complexity. Let's take a closer look at the RBC staging and operation. The design is typically divided into 4 distinct stages, separated by baffles or bulkheads. These barriers help control the flow of water and ensure proper treatment at each stage. Between these stages, there are underwater orifices that allow the flow to move smoothly from one stage to the next. This staged approach is really effective because it maximizes the media's overall treatment efficiency. Now, in the first stage, the organisms face the highest levels of BOD, or biochemical oxygen demand. Because of this, they remove BOD at a very high rate, which is crucial for initial treatment. As the water moves into the subsequent stages, the BOD levels decrease, and so do the removal rates. Interestingly, this is also where nitrification begins, converting ammonia into nitrates, which is an essential part of the treatment process. Moving on to protective covers, these are an important feature of RBCs. They serve multiple purposes, protecting the biological slimes from freezing in cold weather, preventing rain from washing away the beneficial growths, and shielding the media from sunlight-induced algae growth. Plus, the covers help keep the media from becoming brittle over time and provide safety for operators working around the system. Overall, this staged design combined with protective covers helps ensure the RBC operates efficiently and reliably, even under varying environmental conditions. Let's now discuss RBC monitoring and maintenance, focusing on healthy biomass indicators first. A healthy biomass typically shows a brown to gray color, indicating good activity. You'll notice no algae present, which is a positive sign, and the biomass often has a shaggy appearance that suggests good mixing and oxygen transfer. When the coverage is uniform and there are few or no bare spots, it means the biomass is well established and functioning properly. Additionally, there should be no offensive odors, which can be a sign of problems. Now, let's look at some problem signs to watch out for. A black appearance in the biomass usually indicates solids buildup or BOD overloading, meaning the system is overwhelmed. In this case, you might need to place another unit in service or pre-aerate the influent to help balance things out. If you see a white appearance, it suggests sulfur-loving bacteria are active during high loading conditions. During severe overloading, removing the stage 1-2 bulkhead can help manage this. Severe sloughing, or the shedding of biomass, indicates the presence of toxic substances. To address this, eliminate the toxics or dilute the influent to achieve a more uniform concentration. Regarding maintenance, RBC systems require minimal effort. Most moving parts need only minor preventive maintenance, such as inspecting chain drives, belt drives, sprockets, and rotating shafts according to the manufacturer's instructions. It's also good practice to paint exposed parts and bearing housings for protection, and to grease shaft ends and bolts to prevent rust and corrosion. By keeping up with these simple maintenance steps, we ensure the system runs efficiently, supporting the overall health and performance of our treatment process.